Okay, so, uh, what's kind of y'all's level of experience with Unity? None? Nice. Okay. What about you? Kind of? Okay. Like, as in, like, have y'all opened the Unity editor before? Okay. So y'all kind of know. Have y'all maybe like followed some tutorials before? Okay. Okay. I see. I see. That's totally fine. Um, we might go a little bit fast, so feel free to stop and ask some questions. But in general, we're kind of going to like I'll try and go a bit slow. Basically, there's a very loose plan, so there's a lot of kind of adjusting we can do. Um, so hopefully this will still be valuable to y'all. Um, but okay, so if the kind of AI I'm going to be thinking of for this workshop is so you made like a turn-based AI. The kind of AI I'm going to be thinking of for this workshop is like the kind of enemy you might have in like an action game, right? So our goal broadly is going to be to have some kind of enemy that's going to basically chase you, right? Um, so our goal is going to be more how do we get this behavior to be interesting? So what we're going to do is we're going to start off with just a very simple, um, a very simple. This enemy is here. The player is here. The enemy is going to go straight to the player, right? And we're going to see that there are problems with that because when we had multiple enemies, they're going to clump up. It's going to be kind of a mess, right? Um, and then, so basically, I'm going to open it up to y'all to basically try and propose some solutions of how we might try and deal with that, and we'll try and implement some of them. Very briefly, we might talk about pathfinding. So if there's an enemy here, the player here, and the enemy needs to go around a wall to to chase the player. So we might talk about some potential solutions to that. Um, this is a 3D game. It's okay if you ever do this accidentally. You just install the 2D package. So I'll go ahead and do that. Um, yeah, because any any 3D scene is also a 2D scene, or rather, any 2D scene is also a 3D scene. So it really doesn't matter because you can just click on this, and everything is still there. So yeah, no, that's very simple. I just go into here and go something like 2D or just 2D. Still okay. So I'll take a little bit of some extra time. Um, but so once we can talk about some pathfinding. The other thing we can also talk about is how do we add multiple states. So our core focus is basically just going to be we have some enemy that's just always going to do the same thing, right? It's just always going to have one behavior. Um, but there's also cases where, uh, say you want an enemy to attack you, but then if the enemy doesn't see the player, then the enemy should like run away or go and patrol or go do something else, right? So we have this idea of the enemy is in some state, right? But we want to be able to transition between multiple states, and that's a whole coding problem. Um, I should ask, how many of y'all are computer science majors? Y'all, are y'all AET majors back? What majors are y'all for? Physics, nice. Okay. Informatics, nice. Okay. What about you? Same. Okay, nice. So do y'all have kind of a little bit of experience with coding at least? Okay, yes. So y'all will be able to follow along. Um, do y'all have any experience with C Sharp? Do y'all have experience with Java? It's very similar. Syntax wise, it's basically the same. Okay, we have our 2D package in. So I'll go and maybe make a new scene. Where are we? Scene. Okay. I'll go ahead and open this. And then we want this to be an orthographic camera. And these are a little bit extra steps than you might have to do if if you had just made a 2D scene in the first place. What I'm having to do is because I accidentally made a 3D scene. So I'm just setting up like this is what you would get if you opened the blank 2D scene. Hello. You're also new, right? Welcome to our yes. So we're doing an AI workshop today. Um, what's kind of your level of experience with Unity? Yes. Nice, nice. Okay. Um, like, have you made like a game before? Nice, nice. Okay. Um, and also, same question I asked everyone else. Like, have you ever made some kind of game AI? Nice, nice. Do you want to kind of describe more or less what it did? Nice. That's what we're about to start with. So we'll see how to kind of expand upon that as well. Okay, so this is what you would get if you just opened a blank 2D scene. So I'm going to go in here, and I see 2D object square. Okay? And go in here and choose this. I want there. Okay. We'll have to deal with the slightly annoying skybox. I don't know if there's a way to turn. Oh, there it is. Okay. So here's our game. Oops, this square. Okay, so we're going to start off by making kind of a player character just to get everyone caught up. So I'll reset this. And then I want my player to be slightly smaller. If I can type today, we can leave the z-axis alone. This is my player. Does everything I've shown up here kind of make sense? Like, does everything on the screen kind of make sense right now? Okay. So to get our player to move, I'm going to want to add a rigid body 2D, right? I'm going to want to disable gravity. And then I usually do always collision detection continuous and interpolate for this. There is a whole workshop on physics stuff on the EGADS YouTube channel if these settings don't necessarily make sense. But I just like to add them for any sort of player character. But there's a whole workshop where we kind of go into depth on what these do. I'm going to add a collider, just a simple box collider, 2D. And since the default Unity colors are somehow the ugliest shade of blue they could have picked, I'm going to hopefully make this maybe slightly nicer. We'll do something like that. And then our player will be blue. Okay. So everything making sense so far? We know what a rigid body does. We know what a collider does. Okay, nice. So now I'm going to make a player controller. So I'm just going to go in here and add a new script. If you are following along and you want me to stop at any point, feel free to just like interrupt me and say and ask for some more time. But I typically I'm not personally a follow along person, so I don't assume that y'all are following along. But if you happen to like to follow along, then feel free to stop me. But anyways, we need here, we're going to make a very simple player controller. It's going to be top down. We're going to go WASD. We're going to move up, down, left, right. Okay. So we have our rigid body 2D, which we added to our character, so we're going to need a reference to it. Okay. And then we have some move speed that we want our player to move at. Does anyone want to explain what serialized field does? Does anyone know?
It lets you change it in edit.
Yes. Why do we prefer that versus saying public field speed?
Well, it can't be accessed to other scripts if that's important.
Yes, right. So quick detail for those of y'all that are like know Java, but maybe you haven't done C# before. In Java, if you don't put an access modifier here, right, Java does, in my opinion, the silly thing and assumes that this is public. So you have to explicitly put private if you're in Java, right? C# does the opposite. So if you put nothing, then it's assumed to be a private variable, right? Um, but what serialized field lets you do is it lets you change this value in the inspector without making the entire variable public, right? So that's basically the goal of doing this. If you make it public, you can also change it in the inspector, but then you make the variable public, and that's generally conventional wisdom says to not usually do that. But yeah, let's just grab a reference to our rigid body. So we get component rigid body 2D. And then we want some kind of move input, right? So I'll store our move input in a vector 2 called move input, right? And I'll say that move input is going to be some vector 2. We know from previous workshops that Unity has some very handy input axes called horizontal and vertical, which map to x and y. It map the sort of positive x, positive y, negative y directions to WASD and also the arrow keys. So we very simply just have to say get axis horizontal, get axis vertical, and this will be a vector 2 that points in the positive x direction if I'm holding the right key, the negative x direction if I'm holding the left key, and then similarly for the vertical axis, right? So we have our move input, and then I'm going to go into fixed update, and we're going to say that RB dot linear velocity is equal to move input dot normalized time speed. And then if we go back, we should see once this compiles a variable here that we can all set our move speed to something like 5, and then we can move around, and then we have our top-down controller. For those of y'all who are like new to Unity and maybe have done some tutorials, does everything up here kind of make sense? In particular, does this make sense? Yes? Okay. Again, feel free to stop me if you need me to explain something. Speed is a constant that just tells you in any direction I'm moving how fast am I going to move, right? Hello. Welcome. You're also new, so welcome to our Unity workshops. We have a lot of new people. I hope you'll enjoy. What's kind of your level of experience with Unity? Okay, like maybe you've done some tutorials. Like you've done some tutorials, maybe. Yeah. Have you made a game before? You started. Okay, that's good enough. Um, cool. Yeah. So we're basically just doing an AI workshop. We're going to do some very simple behaviors and then try and make it more complex. So everything on here we've just done is all we've done is made a very simple player controller that goes WASD. Right. Okay. So now that we're all kind of caught up there, so our next step is to actually add our enemy, right? So I'm going to go in here, and then very similarly as last time, I'm going to go in here. I'm going to make a square. This will also be 0.5. This is the axis you can leave alone. And our enemies are going to be red. I'll call this enemy. This will also have a rigid body 2D. These I will leave alone for those, and then I'll have a box collider 2D. And then so now that we have kind of enemies that are interacting with each other, what I'll go ahead and do is basically say that our player can't rotate and our enemy can't rotate. This is just going to very simply make it so that, oh, I forgot to disable gravity. We'll go back. We don't want it to fall through the floor. And it does have a block slider. Okay, that should fix that. So basically, we don't want it to rotate when that happens, right? So we're going to start our enemy controller by going in here and adding an enemy controller script. Right? And if you want the enemy to follow the player, first thing you should probably do is get some reference to the player, right? So I'll have a transform for the player. Why am I saying transform instead of game object? I could have said game object, but why is transform okay? Yeah. Yeah. So well, you can go game object. Say this were a game object. You can go like game player dot transform, right? And this lets you do that because transform is actually a public property of game object. But it's like we're gonna be saying player dot transform a lot, right? Because we don't really care about anything about the player except where it is, if that makes sense, right? On the rare occasion that you need to access the actual game object, you can go player dot game object, right? You can reference both from each other, right? But in general, I would choose the more restrictive of the bunch, which is a player, which makes it kind of explicit that what we care about is the position of the player, right? So we have this player. So how do we get a reference to it? Well, it's some other game object, so it's not a component that we can just access. So we can go game object dot find game object with tag, and then we'll find our game object that has a tag player. And of course, this gives me an error because this returns a game object, but this is of type transform. So I have to go very simply dot transform. Okay. And so if I go back here, one thing I have to make sure is that this player has the tag player. The Unity people have been very generous and decided to already include a player tag. And you can, of course, add more tags if you need to. In fact, we'll probably add an enemy tag later on. So we'll go back here. And what we'll basically say is we'll do something very similar to what we did with the player. We want to basically constantly tell the enemy sort of where to move, right? So what I'm going to do is take the difference between the player's position and the enemy's position, right? So we'll make some variable called, before I do this, just to make it kind of clear the structure of what I want to do, we'll have some vector2 called move direction. And then we'll also have some float speed, so like a serialized field float speed, very similar to what we did with the player. What I want to do is calculate what direction we want the enemy to move in. And in fixed update, right, set, we also need a reference to the rigid body. Again, exactly the same as the player. Rigid body 2D RB, and that is just a component, so we can go ahead and get it like this. And then we say RB.linear velocity equals move direction times speed, right? So our goal is to figure out, what is the move direction, right? What direction we want the player to move in, the enemy to move in, right? And then once we do that, it's literally just a matter of updating the velocity on every frame to move in that direction, right? So how do we figure out the move direction? Basically what we want to do, this chair is really low. It's also broken, that's wonderful. So our move direction is going to be the player dot position, right, minus my own position, right, so the enemy's own position, right, we're going to take this and we're going to normalize it. Okay? who wants to explain kind of who wants to break this down and sort of explain this formula here that we have. So why is this the move direction? Yes.
So basically, you are taking the two vectors and subtracting, basically.
Yes.
It's just like, I'm trying to figure out how to explain subtraction. Basically, it's just like you're taking the position and like by subtracting it, you get a new vector that is pointing toward that, and then normalizing it is just making sure it's part of the one, basically.
Yes, exactly. Does the idea of subtracting vectors kind of make sense? Maybe it's helpful to draw a picture. Well, yeah, this is some AI stuff. No one needs to look at this.
Different kind of AI.
Different kind of AI. Ours is the better kind of AI. And also decidability. Ew, we can. Okay. This is the unfun part of CS. We like to make fun games. Okay. I like to carry around whiteboard markers with me, so we can this. Everyone kind of see if I write it right here? Okay. Basically the idea is, let's say this is our 2D axis here. Right, we have, say, here's the player's position P, here's the enemy's position P, right? If you think about it like this, it's not really clear why subtracting these positions would give you anything like meaningful, right? Like what does it mean to do this, right? But when you think about them like vectors, right? So you think about this as some x and y position, right? That not only represents the points in space, but actually an arrow from the origin, right? That goes here. And similarly here, an arrow from the origin that goes here to some xy, right? But basically the geometric interpretation of subtracting p minus e is some other vector whose x and y components are basically this arrow right here. The arrow that goes from e to p, right? So the x and y, we're not thinking about this as a position in space, we're thinking about this as the difference between this arrow and this arrow, which is, or sorry, rather this arrow and this arrow, which is how do we go from this sector E to this sector, right? So we're thinking about these kind of as vectors in space. Okay? Does that kind of make slightly more sense? Yeah. Okay. Oh, and normalizing. Why do we normalize? First of all, what is normalizing?
You get a unit vector.
You make a unit vector, right? So this is our direction. This is like, if I go, basically the idea is if I take E, right? So I'll call this vector that we just got from subtracting, so player opposition minus transformed opposition. I'll call that B, right? The idea is if I go E plus C, I get B, right? That's kind of also an intuitive reason why this is that arrow, because if I take E and then I move it over by B, I get the actual vector, right? This is like what it would take to teleport me, right, over there, right? But what we actually want is sort of an arrow that doesn't really reach there, but points there, right? So a vector of length 1, right? And that's what normalizing does. It takes some vector of any length and converts it into a vector of length 1. Why do we want a vector of length 1? Because then we're going to multiply it by speed. And when we multiply it by speed, say this is of length 1, say enemy moves over with a speed of 3. Now this vector has a length of 3. Right? That's what it means to multiply a vector by some kind of floating point value, right? We're going to take that vector and we're going to think about like an arrow, and we're just going to stretch it out. So that's what the interpretation of move dirt times speed is, just lengthening that arrow. So it was length 1, we're going to make it length probably 30 in the near future, right? And then so now we have a vector of length 3 that moves, that points to P, right? And if we set our velocity to this direction, it'll move in the correct direction with the correct speed, right? Does anyone have any questions? I can explain more if necessary. But does that kind of make some sense? Okay. So hopefully what we'll see now. Uh, uh, hopefully what we'll see now is that if I go into here and set this to, say, a speed of 3, you can see it updating, right? So you can see that no matter what, we just kind of know what direction to move into, right? Because it's just subtracting those two vectors and then moving me over. It might be a good idea, since this enemy is so small, to turn on interpolate, because I'm seeing a slight amount of jitter. Again, if you have any questions about these settings in particular, shameless plug, there's a physics workshop on YouTube, so you can see that this moves. It might not be visible on there. Actually, I don't know if it is visible on there, but it's visible in here that this is smoother. So in this case, it might be worth it to turn on interpolate. Okay, so we did the thing that we set out to do, right? Which was to get an enemy to follow the player, right? And it's actually like very little code. Like this is like 1, 2, 3, 4 lines of like any amount of code. Yes. To what? Oh yes. Yeah. Yeah. If you need to copy something down, feel free. So if we added, say, so okay, we have one enemy working. Now I say that I want to have like 4 enemies. Okay. What would happen? They would all start following you. Um, they all turn into a single big clump, right? So just to kind of demonstrate, are you good with the player? All right. So just to kind of demonstrate what would happen is we have a bunch of enemies here. So they start off kind of spread out, and then I go like this, and then this is pretty much how they're going to stay, right? And then so the entire game turns into me running circles, and then I don't know, this is like some top-down shooter, and I like throw a grenade, and then I win, right? So we don't want that, right? And so this is where things get complicated, right? Who wants to propose a solution to deal with this? There's so many ways you could deal with this, so I'm gonna actually write a lot of them down. Who wants to propose a solution to this? And there's really no right or wrong answer. Like quite literally anything could work, and everything has its pros and cons. Yes.
You can check if they're touching another enemy, or if they are, you just like bounce them away from each other.
Oh, okay. So basically, you want the. So you want to check if they're touching or if they're near each other.
Well, I suppose either can do it.
Right. I mean, either could work.
So they're able to, and isn't by force.
Yes. Yeah. So like one enemy bumps into another enemy, and then they kind of bounce, or they bounce. Okay, so we can do that. Use bounce. So what would kind of happen is you would get a lot of they would bounce and then kind of come back together, which maybe you want. Like you would have a clump of enemies. The enemies go here, and then they kind of would continuously go like this. Maybe is probably what would happen if we started doing that. Any other ideas?
In addition to moving towards the play, I also try and move away from any other enemies that are close to me.
Yeah, yeah. Move away. From enemies close. Right, and then so this is this is absolutely a very good strategy you could take. And then this has a whole other can of worms that you could open here, right? So how do we figure out what enemies are close, right? And how much should we avoid them, right? So we can absolutely explore doing something like this. What's kind of a way that you might implement that?
Well, you could keep a list of all the other enemies that are within some distance of you. You could, I think, take like each of the vectors that would take you like away from each of those enemies. Yes. And then weight them a certain amount depending on how close they are, and then match that together with moving towards the flavor. So that the closer you are to an enemy, the more you get repulsed.
Yeah. So that's exactly right. So basically you want, so you basically want to take all of the enemies around you. So who are my, I don't know how to spell these names. So enemies near me. Right, so we want to know kind of how close we are to them, and there's a lot of ways we could define that. And then we want to basically weight them somehow. And then come up with some kind of some kind of opposite pointing vector, right, that moves you away from, right? So you figure out, basically you do the opposite of what we just did, right? So you would take, remember how we said we want to find the vector from here to here, right? You would find the vector from from the other enemy to here, so we reverse the direction, and then we move it in that direction, right? And we might actually try implementing this in a second, so we might something like that, and then basically move away from that. Right, so how you choose to define weight is also interesting. So one idea is you said look at every other enemy. So what that might look like is sort of finding I'll call it like the repulsion vector, the vector that goes away, right? Finding each of those, weighting them somehow, and then summing them all up, and then going to that. One other idea is to calculate some kind of like center of mass of the nearby enemies, and then moving away from that, right? You might not even, oh yes. You can absolutely use rate tests. I was about to get to that actually. So there's two very like valid ideas here. One is keep a list. So each enemy has a list of enemies that are near it, and like when an enemy goes out of it, it goes out of its list and maybe into someone else's list. Or you could basically just do a giant circle cast and be like, get me all of my neighbors all at once. Which one is better? I actually don't know. The circle cast is easier to implement. That's definitely true. It's what I would do. And ray casting is efficient in any modern game engine, so we shouldn't feel too bad at doing like a circle caster thing. That should be okay. Especially because you don't actually have to do it every frame. You can do it every every half second or so, because enemies don't have to update in real time. But that's basically what I would do. If you wanted to do some kind of list, I guess that would avoid, you would only update it when something leaves, but you'd still have to check it. So I actually don't know. But if it were me personally implementing it, I would just do a circle pass. Because it's probably so yeah, one idea is to get all the enemies near you by doing a giant circle cast, which will give you back a list, calculating the center of mass between them, and then getting the vector that points away from that, and simply sort of adding that on, right? So the new direction, right? If that's a little vague, we're about to, actually I think that would be a good thing to implement. I'll make one simplification to what y'all have proposed. Instead of sort of trying to get the enemies that are neighbors, I'm just going to say that the enemies all as a whole want to move away from wherever the center of mass of the enemies is, right? And the strength of that is going to increase as we get further. So we'll consider all the enemies to be neighbors in this case, right? So actually, let's go ahead and try and implement that. Um, okay. So, um, what we basically have here is we now need basically all of the enemies, right? So, what might be useful here, and this is a common pattern with any sort of AI, right? Oftentimes you have to decide what knowledge does belongs to the AI itself, right? So what knowledge belongs in enemy controller, for example, and what knowledge belongs kind of outside of the AI. So what kind of oftentimes the pattern we have is, and this comes up in multiple kinds of AIs. When you have like, if one day you learn about behavior trees, or if you learn about any other form of decision making for AI, there's often some kind of um, centralized place where each enemy can go and look for information, just global information about the world, right? So what we've proposed here, the global information is where is basically the center of mass of all the enemies? Where's the midpoint of all the enemies, right? So um, I'm going to make a new game object, and I'll call this enemy info, right? Um, and this will have some enemy info script. You call this world info. World info is probably a better name for it, right? Um, I'm debating whether to make this a singleton or not. I'll make it a singleton. I'll do the scary and controversial thing. Um, I'll have some static enemy info instance, and then in the start I'll set, or sorry, rather in awake I'll set instance equal to this. Okay. Um, who wants to explain what I did here and why? Yes. Yes. Exactly. So, and then we have this static variable, uh, enemy of type enemy info. So it's of the same type as the class itself of instance. And then on awake, right? So before any game objects are loaded in, we set instance equal to this, right? So instance equal to whatever the engine just spawned in, right? And then so now if I want to have some public um, public vector 2, and then we'll call this uh, enemy midpoint. Oh, yes. Oh, yes, I can. Oops. There we go. Sorry about that. Um, we can go in here, and we can go into any enemy controller, and I can very simply say enemy info dot, this needs to be a public variable. Public static instance dot instance dot enemy midpoint. And then we can set this equal to, I don't know, var x equals whatever, right? So it's a very simple way of just taking an entire class and saying there's going to be one instance of it. So this is called a singleton, before I get ahead of myself, right? Why is it a singleton? Because typically what you say is this, right? Is there's only ever going to be one enemy info. There's some global enemy info that lives within the scene. And we're going to expose the instance to it to everyone, right? Why might this be a somewhat like scary thing to do and maybe ill-advised?
Because other things happening in the lake that might happen before this happens.
Yes, but in that case, what we might just say is like, um, what we might just say is that, well, nothing in a way can depend on anything that happens in enemy info, right? Um, Basically, the reason people don't like this is because we've taken uh, just the entirety of a class and basically uh, said that anyone can have this, right? You can imagine how this could get out of hand. Like, for example, if we, instead of getting a reference to the player via game object find game object with tag, we just made player a singleton and said everyone can access player, right? Uh, you can imagine how this sort of thing would get out of hand very quickly, where everyone has access to everything. And the reason we don't like that is um, because here I'm having to make it very explicit that I'm getting a reference to the player, right? So I know the enemy controller depends on player, right? On the other hand, here, you're really just burying this in the code, right? You can access it at any time for any reason. So if there's some change to enemy info or something that breaks an enemy info, you could really cause like a domino effect where like everything that uses it, right, and just has direct access to it now somehow breaks, right? Um, so that's a little bit more abstract. Like obviously for this, it's a very simple game, but if you ever come across a singleton, um, some people say never use them. I think they're useful. For example, here, this is a very clear instance of something that should just be globally accessible, and there's only ever going to be one of them, so this is totally fine. There's also no risk of enemy info somehow being destroyed, right? That like this reference now somehow becomes invalid. Like there's no way that's ever going to happen, right? So here, I feel comfortable saying go ahead and make this just a globally accessible thing, right? Um, but there's also ways that this could, if you just start doing this for everything, then that might not be so good, right? Um, but that's kind of a side tangent on singletons. But a lot of game AI, especially when this becomes more complicated, is learning about how to manage state and knowing who has access to what information. And this is just a very clear pattern that usually emerges: is that you have information that's local to enemies and information that is global to enemies, right? Um, So that's a slight tangent, but now we need to basically get um, a reference to. So the whole reason that we did this is because we want access to the midpoint of all the enemies, right? That's the whole motivation behind doing this, right? So in update, what I need to do is every frame, I need to calculate the midpoints between all the enemies, right? Um, Strictly speaking, you don't have to do this every frame. In fact, you probably shouldn't do it every frame. Uh, your enemies do not need to be reacting at 100 frames per second. Like if one enemy moves over like 1 pixel, it does not need to recalculate the entire sum. We're gonna do it anyway for the sake of simplicity. But what you could basically do is add a timer and say, okay, we're gonna recalculate this every half second or so, right? Or every quarter of a second or so. Because it simply does not make sense to always uh, calculate this, right? And also we're going to be doing a very simple, we're in a loop and we're going to sum and then we're going to divide. So we're going to take a very simple average. There are probably smarter ways of sort of aggregating the movement of all the enemies such that you don't have to do a giant loop in the middle of update. But we're just going to get something working for today. So one thing I should probably have is some array of enemy controllers. Or really, we should probably have, we'll make them game objects. Why not? If we want to change the type, we can change the type later. So we'll call this enemies, and this will be a game object array of enemies. So what we'll do is we'll say enemies is equal to game object. We don't want to do this in wake, we want to do this in start because we want everything to have already been spawned in. Equals game object dot find, instead of game object with tag, we find game objects with tag. So this will give back an array of every game object that has the tag enemy. Unfortunately, Unity is not nice enough to already give us an enemy tag. So we'll have to go in here and tag it ourselves. While I'm here, I might as well go in here, call this enemy. So I've deleted all of them, and I'll show you why in a second. I'll add my new enemy tag. I go into here, I add my enemy tag, and I'm going to turn this into a prefab. So this goes in here, and this, very simply, I can go and drag in here, right? So if I now go and I change the color of one enemy, I can go in here and I can say apply to prefab enemy, and now all of the enemies change, right? So that's the reasoning behind doing a prefab, is the enemy now lives inside of our assets folder, and we can simply drag a new one whenever we want it, and it'll have the exact same copies. And if I make a change to one, I can easily make a change to all of them, right? So that's the idea behind the prefab, right? You don't necessarily need all of those, right? So what we'll do in here is go for game object enemy in enemies for each in wrong language. Okay. So then we'll keep some kind of sum. Vector 2, I'll call this a sum, right? And then this will start off at vector 2 dot 0, right? And then so we want the midpoint, or the average position between all the enemies. So we sum this. And this is vector 2. We want to sum, position is a vector 3, so we want to sum the vector 2 of that. We just want the x and y components. And then we just simply divide by however many enemies there are, right? So now sum is the midpoint between all of the enemies, and now enemy midpoint is equal to sum. Yes?
Is there a reason you guys add directly to enemy midpoint?
You could do that. There's no reason. I just want it to be clear that there's a sum. So you could say something like enemy midpoint. We're going to zero that out, add directly enemy midpoint, and then divide equals 0, right? What does that mean? I don't even know. Random C# thing.
You have it defined, but you said vector 2
On line 22. Oh, yes. Thank you. Yeah, exactly. So this will just get the average point between all the enemies. Good catch. Thank you. So now what we want to do is, so we had this move direction, right? And we still want to have a move direction, but now it's more complicated because we need to have sort of the move direction to the player, but also we need to take into account this other value, right? Which is the direction away from the midpoint, right? So what I'm going to do is say that move direction, so this is going to stay the same, right? But move direction is now going to be the sum of two components, right? It's going to be the sum of, right, it's going to be a sum of basically the direction to the target, right? So we'll have, say, what should I call the direction? I'll call this spread out, or I'll call this repulse direction, right? So we have our target direction, we have our repulse direction. So our target direction is just the direction to our target, right? And then, but our repulse direction is going to be, so we want to move away from the center. So we want some, transform.position minus enemy info dot instance dot enemy midpoint, and we want this to be normalized. We want this to be, I should just go ahead and make this a vector 3. We're not going to use the z-axis, but it prevents me from having to do unnecessary casting. So this will be a vector 3, and that's fine. Right, so this will be vector 3.0. The reason is transform.position is inherently a vector 3, so when I subtract it with a vector 2, it's going to get mad at me. So we'll just go ahead and say everything's a vector 3, and that'll be totally fine. All right, so now we have these two, right? but we need to figure out how to combine them. Right? So we know target direction times speed, right, is the direction to target times speed is how fast I want to move in that direction. Right? But we also want to add some weight, or there's also there's other ways you might do this. You could say that speed is like a hard limit, right? Because if you were to do something like, repulse direction times, and then we have something here, serialized field float, repulse weight, plus repulse direction times repulse weight. You can see how what you would end up doing is moving away faster than speed, right? Does everyone understand how this would move faster than speed if you did this? Right? Because this component already moves at direction speed, and then you're adding some other repulse direction that also moves at some positive value. So what you might want to say is that speed is a hard limit, and we're going to basically say, combine these here, right? So we'll combine the two directions to get some kind of, we'll bring back move direction. And then we'll combine this here and basically say that this is target direction plus repulse direction times repulse weight. And whatever this ends up being, we're going to say that RB.linear velocity is just equal to move direction times speed. And then this, of course, has to be always normalized. So I'll say that, just to be clear, I'll say this is equal to move direction dot normalized. Right? So all we're doing here is we've calculated our two values. One is the direction to the player, one is the direction away from the enemies. Right? And then we've weighted this by some constant amount. Right? And it doesn't have to be a constant amount. We'll get to that in a second. And we've calculated our new move direction as sort of the combination of these two vectors. Right? And then we're going to say whatever direction we want to move in, move at some constant like speed away from that, right? I know that y'all mentioned that it should change with the distance to the midpoint, right? We'll do that in a second. Let's just kind of see what this works because we've done a lot of coding so far. So we'll go in here. We're about to, right? So right here we have repulse weight, which is currently 0. And let's just say that we want to weight this about half, right? So however much it wants to move to the target, we're going to weight that by about half as much as it wants to move away from the enemies, right? So go in here and apply. And then let's just kind of see what this does. I suspect this will be somewhat wonky because we're not weighting by distance, but you can see it works, right? So the enemies kind of, you can see kind of hovers, right? It's not like they move and then spread out. It's, I got trapped. I lost my own game. They kind of hover at this kind of distance, right? Because no matter what distance they are from each other, the distance away from the midpoint is always just we're going to weight that by some amount, right? Are there any questions on what we did here so far before we make this a bit more complex? Right, everyone understands, especially for some of y'all who might be newer to Unity. Everything is making sense. Yeah, that's great. Okay, I'm glad that we're all following along. So I can add more enemies, and it's just going to handle it just fine, right? Right? Maybe it can't handle so many enemies because we are doing a somewhat wonky for loop, but I'll leave that as, I guess, an exercise to the reader of how to make that bit more efficient, right? But you can see we kind of spread out. You can see that the kind of interesting property that's kind of emerging here is since we don't care about distance, it's just kind of hovering at some constant radius away from, and as I spread out, that radius increases as I kind of get closer to the enemies, right? You kind of get this behavior here. There's always some constant radius, and they just kind of hover around that. They form kind of a circle, right? So that's kind of interesting. I didn't expect that to happen. So now let's try and kind of weight this by distance, right? So instead of just by a constant repulse weight, we will do this basically based on the distance. So we'll do repulse weight, and we want this to increase by however much the distance is from the midpoint. So what we want is, before we normalize, is to get actually the length of the sector. Right, so we'll say repulse length, and I'll make a new variable here. Or we'll say distance from midpoint. And very conveniently, the distance from the midpoint is simply repulse direction length or dot magnitude. Wrong game engine. Direction dot magnitude. Oh, this should not be vector 2. My bad. Float. Okay, so our float distance from midpoint is simply a magnitude vector. Magnitude is another word for just the length of the vector, right? So however long that vector is. So remember last time we had, I erased the image, but remember we had sort of the arrow going from one point to the other. However long that arrow is the magnitude of that vector, right? So what we get there is repulse weight times distance from midpoint, right? So as the distance from the midpoint increases, right, we're going to weight this, right? And so this is going to, as the distance increases, the repulse weight is also going to increase with that. So we need a significantly smaller repulse weight, right, in order to not completely blow this up, right? So this is one way you could do it. There's plenty of other ways you could try and weight by distance. This is just a very a simple one, and we'll see what result it gives us. Divide by distance instead of multiplying. Oh, you're correct. Yes, we want to divide by distance because the closer we want, basically, the larger this is, right, the smaller the weight, the overall weight will be, right? So as distance increases, this whole fraction will decrease. So then increases. As this approaches 0, this will increase, and then so we'll have a bigger weight. So yes, thank you, good catch. What we would get the opposite of, where they would want to spread out more, and I think they would all just run away from each other. So what we'll get is here. We'll go back to our 4 enemies, and then so what we really want is quite a small repulse weight. So we'll see what happens there. See it? They're kind of not really doing anything. Let's try increasing repulse weight. Let's make a really big repulse weight. Yeah, so now they kind of settle into a different pattern there. So you can see that maybe I go down to, say, 0.25 or something like that, or 0.3, right? There's a little bit more variation in the movement because as they get closer, they're going to more aggressively try and move away from each other, right? So if I have these different clusters of enemies here, I can have these, and we can see what kind of sort of behavior this will produce. Maybe increase this slightly. Because they're all quite far from the midpoint until they get to here, and then they kind of spread out like that, right? So at this point, with this many enemies, this is an argument for doing it locally, right? Because what would happen is this cluster would calculate its midpoint, this cluster would calculate its midpoint, this cluster would calculate its midpoint. We have one global midpoint, which means the midpoint is right here, right about, right? And then so they're all like, well, I'm pretty far from the midpoint, so I don't need to move that far, right? So that's why we're seeing a reduced effect when we have more enemies like that. So let me try and make one cluster and keep it to just one, right? We'll spread these out here. And we'll add like one more here, right? and then we'll try and see that effect. Play, apply here. Right, so we can see that that's kind of the midpoint, and they're kind of moving away from each other, but then they're also kind of forming their own clusters, right? So the fix here would be to not consider these all one cluster, right? To do some kind of circle cast, and then they each calculate the enemy, their own local midpoint. Does everyone know how to do a circle cast in Unity? No? Okay. Yeah.
Physics, overlap sphere, something like that.
Exactly, yes. It is exactly that. So the way you would do this, we won't implement this, we'll move on to something else, but exactly the way you would do it is you would say, so in the same way that we got our enemy midpoint here, we would say, we would have a game object of enemies nearby enemies, and we would quite literally just say nearby enemies is equal to physics 2D dot overlap circle all, right? And this takes in several parameters. So the first one is the point, which is the origin of the circle, right? So this is transform. We might just end up implementing this by doing this, so that'll be fine. We'll have some radius, so some neighbor radius. Neighbor radius. I think that's. I don't know how to spell. Spelling is hard. So we'll have some neighbor radius. And then we have this different thing, which is a layer mask. Has anyone here not used a layer mask before? Yeah, okay. So what a layer mask is basically, so it's kind of like a tab, but it's going to be used by the physics system instead of just like finding game objects, right? So we'll make some layer mask called enemy layer, and then so our layer mask will simply go in here, and then this gives you a collider 2D array, right? And what you can do now is exactly what we did here. Is we would have, instead of here, we'd have some midpoint. So we would have our vector 2 near, I'll call it a cluster midpoint. All right, we have our cluster midpoint, and so we would have our cluster midpoint is equal to vector, we'll say it's a vector 3, 0, because why not? And then for each collider 2D, for each collider 2D, call enemy in nearby enemies. We'll say that the cluster midpoint plus equals enemy dot transform dot position, because we can access the transform from any component. So even though this is a collider 2D, we can just go ahead and access its transform. And then we'll divide cluster midpoint divide equals nearby enemies dot length. Right. So we have this, and we'll clean up this code in a second. So we have this that does exactly that. I'll stick this kind of at the top of the update function. And what will happen is now distance to midpoint, distance from midpoint is, we'll still calculate that there, because then this will go, instead of enemy midpoint, we'll take cluster midpoint. And now we have no use for enemy midpoint because this entire class only existed for having some global knowledge, right? Now all of the knowledge is local, right? Which is what we want for multiple sort of clusters to exist, right? So each enemy has its kind of local cluster. And so we would have something like this, where we go, we sum them all up. And then so now our repulse direction is from the cluster midpoint, and the distance from midpoint is this. and then everything pretty much stays exactly the same, right? Um, what would happen if an enemy was in a cluster all by itself? Nothing, right? I mean, the reason is because distance from midpoint would simply be 0, right? Because uh, transformed opposition would be equal to exactly cluster midpoint, which means repulse direction is just a 0 vector, which means distance from midpoint is 0, which means uh, this would fail, right? So, which means this would get a divide by 0 error, right? So we need to basically account for that, and basically, honestly, the lazy way to do it is just say plus 1. And that'll be fine. Or distance from midpoint plus like 0 point. Or distance from midpoint plus 0, 1. But we also have, right? So basically what you would say is, if it's 0, you really don't want to do anything, right? So the reason is because if that distance is 0, then we're kind of adding an infinitely large weight, right? So that doesn't make much sense, right? So kind of there are multiple ways you could set this up, but the way I'm going to do it is basically just say if distance from midpoint is greater than some threshold, 0.01 seems like a fair enough thing to do, then so if distance from midpoint is some positive value, right? Only then will we go and say move direction plus equals repulse direction times repulse weight over distance from midpoint, right? Does that kind of make sense why we had to do something like that? Right, because if it were in a cluster by itself, then moving away from it would mean it's like all of the enemies in the cluster are like right on top of each other. There's also probably a way to do this to weight this by how many enemies there are. So there's another way you might do that where you also factor in you repulse more if there are more enemies, right? So this repulse weight would then go into times enemies times nearby enemies dot length times some other weight, right? So you could make this formula as complicated as you want, right? And then you would not have the problem, because if the enemies were simply 1, it would be something like nearby enemies minus 1. So this would be however many enemies there are, however many other enemies there are in the cluster, you multiply that by some weight, and then you also add that. So we're making the formula more complicated, basically. And then you would not have to do the if statement, because this would be 0 for one cluster, right? But actually, let's go ahead and do that. Why not? So we'll say repulse direction. So move dir plus equals repulse direction times some repulse weight. So we'll call this a different value to be more specific. We'll call this a distance repulse weight, and then we'll call this a cluster size repulse weight, right? So now we have 2 factors that go into how we move apart from the enemies. We'll have, so our distance repulse weight, which I can go in here, and for the sake of not dividing by 0, because there's still a risk of that, we'll go and add a plus 1 here, right? That's completely arbitrary. We simply adjust the weight accordingly. And then we go and we multiply that fraction by, and here I'll make this more obvious by going down here. We go and we multiply that fraction by however many other enemies there are times the cluster size repulse weight. Okay. Does this formula kind of make sense, what we're trying to get at here? Does anyone have any questions or want me to explain more? Yes.
Did you also put the speed variable back in, or that messed it up?
You could have always put the speed variable back in, right? But you're always going to have the issue where, like, if I only calculate speed here, if I only limit target direction to move at speed, any non-zero vector that I now add on to move direction is going to increase the length of the overall vector. If that makes sense, right? So that's why we keep it here, is because no matter what we wanted to move at a constant speed, right? So,
I think
yes.
right now is there a difference between distance repulsor and cluster size repulsor? Because they're both just in the same product, right?
Uh, so you're correct. What we would do is, so the reason basically is, right, if any one of these is zero, so are you suggesting to add them?
Well, it's just that I don't know if because they're all like going to be multiplied together, right? They can
Yes.
calculate over something times something, and then cluster size repulse rate and distance repulse rate are having the same effect, right? But they're both just elements in a product.
They're having the same effect, but you could imagine, basically, so there are two variables. Basically, our formula here is, right, whatever the direction away from the cluster midpoint is, right, times, so some weight based on the distance, times some weight based on the number of enemies in the cluster, right? If you increase any one of those, you would increase the whole thing, right? So they're having the same effect, but you could imagine that for some constant, if we hold distance constant, what this would do is basically say, well, if there are more enemies, then they should be even more spread out, right? And if you, on the other hand, hold cluster size constant, then the closer they are, the farther apart they should move, right? So you can hold, there are two different variables that are influenced by different things. One is influenced by distance, the other is influenced by cluster size. They're both affecting the same variable. They're both affecting repulse direction. They're both affecting how much weight should we give to this repulse direction. Does that make sense?
Yeah.
And the benefit of multiplying them is if any one of these is zero, then we just don't repulse at all, right? So, for example, what will happen if an enemy is in a cluster by itself is that nearby enemies dot length minus one is going to be zero, right? Because if the length of the array is only one, so then we just don't repulse, right? And then so all of that information is kind of contained within this. So this is the number of other enemies, right? Let's see if this works, first of all. And the more variables you add, the more tuning this comes in. This is where the game design aspect of it comes in. Let me just make sure I haven't totally broken anything. So I want our distance repulse weight. I'll keep that at 0.5. And then we'll add about 0.25 per enemy in the cluster. Oh, and I forgot to apply this. So there'll be a big zero for the other ones. So apply and apply. Oh, I've broken something. Okay. So what we need to figure out, oh, of course, because neighbor radius is zero, so every enemy is in a cluster by itself, right? Actually, that shouldn't break anything because we still would have target direction. Pulse direction. Okay. And this is the part of the night where we start debugging. So, well, first of all, this is broken in many ways. We'll do serialized field, layer mask enemy layer. And then, so we'll have a layer for the enemies. And each enemy object has an enemy layer. Apply prefab enemy. And then so we'll have this here. But I am interested in knowing why, even with a neighbor radius of zero, it doesn't follow the player. Because the meaning of that should just be, well, we should just follow the player because there's no repulsing to do. So I am interested in debugging that. So we have our nearby enemies. We calculate our cluster midpoint. Our target input is here, player dot direction times. If any of y'all have any ideas, feel free to let me know. So we calculate our target direction. Move input is target direction. Move direction plus equals some repulse direction, right? So I'm interested in seeing is if move direction is non-negative here, right? So let's see what that value is. Oh, okay. So some other thing was broken. Uh, okay, we'll accept that. And so you can see they don't repulse from each other because the neighbor radius is 0, right? That's interesting. What did I fix? Code sometimes just works that way. But yeah, so I think literally the only thing we changed was we defined this and we defined some other thing. I don't even know. We'll accept it. But the proof that this works is in if we get rid of one, if we get rid of everything but one enemy, right? This should still work perfectly fine, right? So we're not relying on the repulsion, right? So let's add a couple more enemies. And then let's hope we gave this some like reasonable weights, right? And then this is where you would start to tune them. So we go in here, and you can see that maybe we need to increase our cluster size a little bit. Oh, because our neighbor radius is still 0. Okay, so our neighbor radius will now be, what's a good value? 2.5. So then, thank you. Yes. So I need to go in here. I tried to be sneaky and do it in play mode, but that probably doesn't work. So okay, you can see that they work here, and maybe we need to give more weight to. That's not applied to all the prefabs, so maybe we need to give more weight to the distance. Repulse weight here, and maybe this should be actually a non-negative value because that would decrease. Oh my god, I don't even know what that is. Okay. So this is where you start tuning, right? So you go here, and then maybe they get close, and then they kind of move apart. They're still clustering, which is kind of... They're kind of not, yeah. This is where you tune a bunch of weights. This is where you sit here and you tune a bunch of weights. So maybe distance needs to be valued a little bit more here, right? And one thing to note is we can go as crazy as we want with these weights because the whole thing at the end of the day is normalized, right? So as long as the two weights are kind of proportional to each other in some reasonable way, the whole thing's going to be normalized anyway, so it doesn't really matter, right? You just don't want them to be so crazy high that then you need to add a separate weight function for the target direction. So actually, it might be worth it to... Maybe it would be worth it to... Because when you're adding them, normalizing, there's some way that you could probably balance this with the actual length of the target direction. Because the target direction is itself normalized. Right? So the distance to the player is not being taken into account. But then repulse direction could possibly be a very large value. But then it doesn't matter because they would all be normalized. Never mind. I don't think that would do anything. Oh, now they're being kind of... Oh, because they're all right at the edge of that radius, right? So that's kind of probably because we're weighting distance too much. So we'll say something like maybe 1, and then 5 here. Or maybe it should be like a 0.75. And this is quite literally just messing with the formula, right? We're going to try and get something that looks somewhat reasonable. Yeah, I like that. You see they kind of come together as they get closer to the player, then they come apart as they spread out, and then they kind of get farther apart, right? And then here, they all kind of move towards me. I'm reasonably happy with that. But basically, the improvements that you would make on this is either getting some better formula for how we should repulse, or by tuning the weights, and that will simply come with a lot of trial and error. But the whole reason that we did this is because we now want to be able to have multiple clusters and have it behave in some reasonable way, right? So hopefully now what we should see is that they kind of form their own clusters. You see they're kind of shaky, right? Because uh, they have that weight of, so there's some enemy that's in the cluster, some enemy that's not in the cluster, right? And then they're constantly going in and out, right? So you could probably adjust that and maybe weight number of enemies in the cluster to be a little bit less, to maybe not get that effect to be so drastic. Let's try for here. Let's just try 2 enemies like right here. So we have this, and then they all kind of form one cluster. And then that gets weighted a lot more. My suspicion is that this value is too high, because then that would completely dominate the distance repulse weight. But we'll see. Something like that. And then maybe we go and we increase this.
Can I suggest to change the formula?
Yes.
So I think maybe instead of that line on 48, we want in parentheses 1 plus that line of 48.
1 plus that line of 48. So the effect of that would be, and of course this will, something like this.
So you have sort of the repulsion, and then it gets stronger for each additional enemy.
And then it gets stronger for each additional enemy because, oh, so it'd be 1 plus however many other enemies there are. Oh, so it would be something like this, right? Times, like that?
Yeah.
Yeah. Okay, that's a good idea. Plus 1 minus 1. Oh, right, I did. Right. So what would be a change to the formula that could maybe, because when an enemy leaves a cluster, right? You could decide to do something else, because when an enemy leaves a cluster, it's going to immediately rejoin a cluster, right? So you're going to get that kind of shaky effect. Maybe the if statement idea wasn't so bad, right? Where you kind of consider the distance from midpoint here, and instead of considering this cluster, you would just like not repulse if there's only one enemy nearby, right? Because then you don't have, because maybe the mistake here is to treat it like there's some discrete cluster that you leave in and out of, right? So it should all move away from the local midpoint based on whatever it is. But you would also kind of run into a problem there. What I think you would have to do is potentially, and of course, this is, there's any way that you could do this, has its pros and cons. Maybe you would have to do the nearest like n enemies. So you would have to keep track of, for every enemy, what are my nearest n enemies, and you would have to do something like that. There should be a way to maybe not get such a shaky value from that. There's also other ways to repulse versus just moving directly in the opposite direction. There are other ways we could do that. But yeah, so there are lots of different ways you could do this. We'll stick to this, right? And we'll basically say something like, and we'll try and keep the weights such that it's not so big of an issue, right? Why is it expecting? Here, oh, these parentheses are necessary. Okay. We can maybe try and keep this weight down such that it's not so much of a problem. Uh, and maybe we prioritize the distance weight. They're kind of doing it, right? It's interesting that these have kind of formed a cluster here. Maybe this might be too small. Kind of go in here and say this is. Right, so I think these have formed a cluster. Oh, you know what it probably is? So let's take this frame, for example. Or there was a better frame. Yeah. So this would add another level to the formula basically. Um, but let's take this frame for example. So all of these are part of one cluster, right? Which means the midpoint of that cluster is right here. So we just run into the same exact issue, right? You would need to not repulse from the distance to the midpoint, but you would need to do basically what was suggested earlier and repulse based on the distance to each individual enemy, right? So actually, let's maybe try and do that. So one idea is to, because we considered the whole thing a midpoint, so it's like, okay, well, I'm moving away from the midpoint, but all of them are moving away from the midpoint in the exact same way. So the other way of doing this is to basically, we can go in here and accumulate some repulse direction, right? So instead, what I want is to go and say, instead of treating this as the midpoint, we'll look at all of our nearby enemies. And we might even consider, at that point, not even using the circle cast. At that point, we might consider bringing back this and looping through every enemy, right? And then summing the weights like that. So let's actually try that, right? So instead of enemy midpoint, I'll leave that there in case we want it later. But I'll make this game object public, right? This game object array public. And what we'll do in here is, instead of overlapping circle, what we'll do is for each enemy, for each game object enemy in enemy info dot instance dot enemies, right? We want to kind of accumulate this repulse direction from the individual results of the distance, right? So we'll have repulse direction. I should not redefine that. This is going to be vector 2 dot 0. All right, so we'll have repulse direction plus equals we'll have some distance variable. That way we can properly weight it, right? So we'll have some vector 2 direction is equal to transform dot position minus enemy dot transform dot position, and then we'll say that repulse direction plus equals dir times, and then here we'll have our distance repulse weight. And then what we'll do is we'll kind of divide that. We'll just normalize it. We'll just say repulse direction dot normalize. Or actually, we don't want to do that because then it's always guaranteed length of 1. So we'll say repulse direction divided by nearby enemies dot length. And then this will be number of other enemies. We'll keep this to enemies.length because I don't want to deal with the divide by 0 case. So we'll divide this. And then, so now we have our move direction can very simply be our target direction plus our repulse direction dot normalized, right? And then so now we're weighting each individual distance between enemies, right? So what would happen there is we're hoping that this problem goes away, basically. We're hoping that we're not just treating it like a cluster and that there's going to be two enemies moving away from the cluster but in the same direction, but that each individual enemy is trying to move away from every other sort of individual enemy, right? So let's go back here and then try this. So now you might imagine that this has to be quite a bit smaller. Let me just make sure. Oh, distance divided by repulse weight, because distance weight divided by direction dot magnitude. Because, so plus equals dir dot normalize times, okay, yeah. So we want to take the direction, we want to normalize it, then we want to multiply it by some weighted function based on however long that distance was. Okay? So we'll go back here. And then all of that looks okay to me. That's probably a bit too high, so we'll go 0.25. And our neighbor radius doesn't matter, and our cluster size doesn't matter. Okay, because we're just taking every other enemy. We have a null reference exception from here. We have a null reference exception at line 38, repulse direction. Oh, nearby enemies is not getting used. Right, we'll change this. All right, let's try and increase the weight. I feel like they're moving towards each other. Did I flip a vector here? Yes, I did.
Yeah.
I did. Yeah, so they got closer and then they decided to move towards each other. Transformed opposition. There we go. So you also now know how to make enemies that move towards each other. Let's try this with a slightly smaller weight. You're still kind of doing it. Oh, you're absolutely right. I forgot a parenthesis here. Thank you. Yes. Catch. And then this is correct because we want to move. I had it right before, yes. All right. Third time's the charm. We'll see. Okay. We'll see. Well, so our target direction. So what's probably happening is so maybe we get a vector that points in that direction. So one thing I want to see is that target direction is still positive. Because it could be the case that repulse direction is so large that it's just canceling everything out, which could be possible. Yeah, so one thing that could be is we'll print out here is print out the repulse direction. So what might happen here is not a number. Okay, that will do it. So why are we getting not a number here? We have a repulse direction divided by the length of this. Now, why might that be 0? Unless direction dot magnitude is 0, and I'm not checking, because I didn't go if enemy is equal to game object, continue. Right? So what was happening before is direction is the 0 vector for the enemy itself, right? Because the enemy is at the same distance from itself. So we're dividing by 0. Any float divided by 0 is not a number. Therefore, move direction is not a number. Okay. Attempt, I lost count. But this time, hopefully, should work. They're kind of repulsing. Let's increase the weight. I'm happy with that. So you can see that they all kind of want to follow the player. So if I get really close to the cluster, they do that, right? But as I spread out, you can see they're going to try and also spread out there. Right, so they're all kind of staying together there. And if I have a bunch of separate clusters here, we should get no strange clumping between enemies there. So I kind of come in here, I kind of form this, and we can actually probably increase the weight here. All right, so I'm actually thinking that this probably needs to be some value greater than that, to maybe sort of we'll go crazy. We'll go 5. We'll make them really not want to be near each other. Because we're dividing by distance anyway, right? So it's like they're not going to start repulsing until they're quite far away from each other. And so we see something like this. And then so this is some really large avoidance between enemies, right? So now I definitely can't do the run around in circles thing. And then they find me and then they start doing a little dance. All right. So if you increase the repulsion weight a lot, you get some a bit more interesting behavior here, right, where I really have to try and avoid them. I actually probably have to go between them now. So this is what you want. It's like it's a little bit more interesting than simply having to. They do kind of surround you. Like I actually can't avoid them. This is not me hyping up my enemies. Like I actually can't avoid them. Like if I try it, no, like it's actually, yeah. So this is a way that, instead of forcing a player to run around your enemies, you have to kind of force them to fight, right? So the solution there is just kind of increase the repulse weight. So you can mess around with any kind of formula that you want, right? So that's one way of doing this, right? Just kind of sum up the individual weights. You can also come up with lots of different formulas. You might make the argument here that we shouldn't be iterating through all of the enemies necessarily, and maybe there's still some clustering you can do. Because if you have a bunch of enemies, you're probably going to be doing some unnecessary adds and stuff. Um, so this is one possible implementation. Um, what more could we do, right? If we want to make some more interesting behavior, we could have them because you can see that they all kind of, as you move, they all start to form into one cluster that's more spread out, right? The other thing you can do is make them deliberately choose um, like specific groupings with each other so they can have their neighbors and we can see that the neighbors actually want to stick together and sort of pick different locations. So like let's say here where we start off with this, we could say we could have some way to say that okay, these are going to be one group, this is going to be one group, this is going to be one group. And then we make our formula even more complicated by saying something basically like, well, the enemies want to be close to the enemies in their group, but far away from other groups, right? So then the hope there would be something like, you know, we have like kind of different like squads, right, of enemies that do that, right? The other thing you might actually want to do is increase the amount that enemies spread out the closer they get to the player, right? Um, so right now we're just kind of adding these. We're adding target direction or we're adding repulse direction, right? One interesting thing you could do is you can make these sort of not independent of each other, but instead you could say that the farther away I am from the player, the greater I want the repulse weight to be. Why might we want that?
So they fan out while they have this.
Yeah, exactly. So as the enemies approach you, they spread out, right? And so that's another way of doing that. So because um, right now they kind of spread out when the player is farther away, right? So that I guess relatively the repulsion is worth more, so they tend to fan out as the player gets farther away from them, right? Which is kind of why smaller values of this is kind of why smaller values of distance repulse weight didn't really work. Like if we go to 1, right? Like this is kind of why these smaller values kind of didn't work because you can see that they kind of form one cluster, and as I get close, they kind of prioritize chasing me, and then as I run away, then they start to spread out a little bit more, right? So actually, you might want to do the opposite. You might want to say the closer I am to the player, increase this repulse weight as much as possible. Yes.
Could that be done with one of the, sorry, Jesus. Could that be done with like one of those like curves like that I see sometimes as like a variable property?
Yes, absolutely. So you're mentioning animation curves. Um, we actually could have used animation curves for any part of this. So this is a very simple linear relationship between like um, between magnitude and repulse weight. We could make this a curve, right, and say evaluate it at this curve, and that's how much the weight should be, right? So just as a reference for some of y'all that don't know how animation curves work, so I can define a variable of type animation curve. We'll call this some curve, right? And contrary to the name animation curve, they don't need to be anything to do with animations. They are just arbitrary curves, right? So I can go in here to this enemy. You can see we have this object of type curve here, right? And I can go in here and I can make any arbitrary curve I want, right? And when I make these arbitrary curves, you can see I can add keyframes here. I can change the shape of the curve. I can make some square curve. I can make it, the default is basically like a cubic Bezier curve. I can make it linear. I can make it like this. I can make it like this. I can make any values I want. So I can move out here and I can say that this goes to 3 over here. I can increase here. And I can basically make any arbitrary curve, right? So when I do that, I can go into my curve and I can say curve dot evaluate at something, right? So I can make a curve that has some relationship between distance and weight. So I can say that instead my repulse weight should be uh, curve dot evaluate at distance dot magnitude or at dir dot magnitude, right? So we're definitely not bound to a linear relationship here. And you could have done that for any one of these variables. We just did linear because it's simple. You just divide, right? Uh, but does that make sense to anyone who hasn't seen animation curves before? It's just any arbitrary curve that you can evaluate at some point, right? So yes, thank you for bringing that up because that lets you as a designer have more control, right? So you might want to do, like, if the enemies are really close, then you might want the weight to be like really massive. But if the enemies are far apart, then you might just make the weight to be kind of like non-existent, right? Um, so that's a good point. Thank you uh, for bringing that up. Um, but yeah, that's another thing we could have done, right? Is sort of define this notion of a group where the enemies try to stay within their group but also away from them. Uh, I think the most immediate improvement we could make to this is to have the enemies fan out as they get closer to the player. So what we could do, what you suggest, and basically say uh, the animation curve, we have some animation curve and it's influenced in part by how far away we are from the player. Um, any other ideas of things we could improve?
If we want them to sort of like encircle, we can have the Fulvian act like perpendicular to the vector to the player.
Yes, exactly. So that's another thing we could add, right? So the nice thing about this method is we have some final move direction. Notice this entire time we never touched fixed update, right? Because at the end of the day, the only thing we're concerned with is the same thing we were concerned with at the start of the workshop, which is calculating move direction, right, and moving at some speed. So you can make a combination of as many different vectors as you want, right? So you can add also like some sort of like flank direction, right, that moves perpendicular to the player, right? Um, and so then you want to nudge it in the direction of kind of trying to surround the player. Does that kind of make sense? What he's suggesting? So you would add another weight to that, and then you have the other problem of tuning those weights and trying to get it to be trying to get that to be interesting. So as absolutely a different thing you can add. Actually, that would also make it nice. So like instead of just fanning out, they also encircle the player, right? There are other things that people do. Sometimes another thing I've seen people do is they define some distance that once the like and this is where you would start getting into more complex AI. Is basically you define some distance from the player. So like let's say this is a player, right? And then here are my enemies. So their solution to this is not to sort of do the vector combinations that we did here. The other potential solution to this is to basically say, okay, at some distance away, just chase the player, right? Don't do any of the fanciness we just did, just try and chase the player. But once you get within a certain distance of the player, you enter a different state, which is to encircle around the player, right? And then you could have strategizing between the enemies where you say, okay, for all of the enemies that are in this circling state, right? One of them gets to attack the player at a time. So you have one enemy that maybe this one goes in and attacks and then maybe retreats, and then this other enemy goes in and attacks. Right? So that's another way of also dealing with the same issue of just instead of trying to get instead of just trying to improve the chase state, you just say, fine, chase the player, but then once you get into here, we're going to have a new state, and we'll define it like that. So that gets into something we didn't have time to cover in this workshop, but how we add multiple states. So maybe potential future workshop is sort of taking this and adding multiple states to it. So we might consider doing an implementation like that during the workshop, right? The other AI-related workshop is, remember I got up on the board earlier and I said, how do we fix this clustering problem, right? And we basically took like the first suggestion, right? Um, what I just said would be like suggestion number two. If you'll look on the EGAD's YouTube channel, there is an AI workshop from the previous year. I can't remember if it was the fall or the spring, or the spring. It might have been the fall, so like fall 24. It's either fall 24 or spring 25. Um, where this is also basically the same workshop, but the solution is entirely different. Um, I have a couple minutes, so I'll explain what that basically does. So if you're interested in seeing a different way of doing this, we get a completely different behavior where basically when we chase, we have different enemies, right? So let's say here's our player, right? We define some target position, and we pick some random points around the player, right? It is some distance away from the player, and each enemy gets to claim some target position, right? This enemy claims this target position, this enemy might claim this target position, right? And then so they all kind of go to some point around the player, and then once they get to their target position, then they like, attack the player like this, right? And there's a whole bunch of other considerations you can have with this. So the cool thing about this is here the motion is like smooth, right? They fan out, and then there's kind of a smooth transition between states. Here you get the interesting effect where the enemies sort of very abruptly change direction, right? And you're not limited to just doing one radius of points, right? So if you're interested in more details, I go over this more in that year's workshop. But you're not limited to just one radius of points. You have multiple radii of points, right? So now it becomes, this is getting somewhat messy. You have some enemy here, pick a point on the outer radius, pick a point on the inner radius, and then go straight towards the point, right? So what you get is basically each enemy claims a different spot, and you get this kind of shuffling effect where they go, and then they switch positions, and then they keep switching as they move towards it, right? And so that also deals with the clustering problem, right? And the interesting thing about this is every once in a while you can tell the enemies to shuffle their points. So you'll have enemies that are chasing you, and then suddenly they'll all sort of shuffle and then switch to new positions, right? So that's an entirely different behavior that also deals with the same problem, right? And in that workshop, I also cover how we might do pathfinding, so how we could sort of generalize this, also have some system that moves around walls, right? But yeah, so it is probably 8 o'clock now.
4 minutes till.
4 minutes till 8 o'clock. Let's see. But yeah, so the point here is there's like basically a million and one things you could do to get to that position. That's basically all I wanted to cover today. So thank you all for coming. If y'all are interested in this, feel free to go to more workshops. We do these basically about 5 times a semester. I will be here for a few more minutes if y'all want to ask questions or suggest a different approach we could have taken. Also, all welcome. So, yeah, thank you all for coming. We'll see y'all next workshop.